Uh, let's get let's get started.
All right. Well, good afternoon, everyone. It's a big pleasure to introduce Nathan. I think everyone knows him, so the introduction is a little redundant, but I get the privilege anyway. Nathan, I met Nathan when he came to preview day. I don't remember when, but I immediately enjoyed discussing things with him, and that's continued pretty much throughout the entire PhD. Nathan has been incredibly productive as a PhD student, and I think in his first, and Nathan, correct me, but I think it was your first week you already committed some firmware code for like motor control. So I think that sort of set the pace for the rest of the PhD. I think everyone enjoyed having Nathan around. He's been a good team member. He's always looking for the humor in something, which I think I really appreciate. And he's our first graduate with a PhD from the Hyperlab. So for that, I think, it makes me very happy. And of course, I was hoping to be able to crack a joke about if the presentation is acceptable, but Yao has totally undercut that. It seems even if the presentation is bad, he gets to leave. So anyway, he's going to join Skydio. So if you haven't bought shares in Skydio yet, I suppose now is a good time to buy it. I'm sure he'll continue to do fantastic things there. Nathan, over to you.
All right. Yeah. Thanks for the introduction. Of course, super excited to be presenting on my work with all of you. So of course, I'm a bit sad to be leaving Berkeley. You should be able to see my screen. Let me know if you can't. And then I guess, yeah, feel free to ask questions throughout the presentation. I kind of prefer more of a discussion rather than just talking at a brick wall. Also, I can't see the chat. So if you ask questions, just, speak up or somebody ask one in the chat if somebody could just voice that. So if there's no problems, let's go ahead and get started. There we go. So in case anyone's unfamiliar with what a quadcopter or quadrotor or multi-rotor is, basically these are a type of aerial vehicle that has typically 4 propellers capable of performing vertical takeoff and landing, hovering, as well as some very agile maneuvers. So as we've seen kind of over the last decade or so, these vehicles are able to perform a lot of different really useful tasks. So for example, they can do some search and rescue tasks, building inspection, package delivery, cinematography, and the list kind of goes on and on and on. So kind of the idea behind this talk is that given that this quadrotor design is already been proven to be pretty useful, we're kind of want to look at the ways that we can incrementally modify and improve this design, as well as the control of these vehicles, such that they can be even more useful in specific situations. So there's 4 big ideas that I'm going to be covering in this talk. In the first half, which I show on the left, I'm going to talk about 2 novel quadcopter-like designs that I've developed. So first, I'm going to show how increasing the angular momentum of a quadcopter via an added angular momentum wheel can improve the torque disturbance rejection of the vehicle. And if these videos are a little hard to see, don't worry, we'll watch them in much more detail later on in the talk. And then after that, we're going to look at a second type of vehicle that's able to change its shape mid-flight, and then we'll discuss how this enables the vehicle to do several different tasks that a normal quadcopter wouldn't be able to accomplish. Then in the second half of the talk, which is shown on the right here, I'm going to discuss 2 novel collision checking algorithms that I've developed in order to enable autonomous flight using computationally constrained hardware. So more specifically, I'm going to first talk about an algorithm that's shown here, which is used to detect when a candidate quadcopter trajectory is going to collide with a convex obstacle, and how to do that very quickly. And then in this second project, I'm going to look at how we can extend that type of collision checking into environments where you have previously unseen obstacles. So where you're using, in this case, depth images from an onboard camera to navigate through environments autonomously. So before we dive into the details, it's important to just kind of highlight some of the key parameters that affect quadcopter designs, just so everyone kind of has an idea of what are the things that we want to be thinking about when we're doing these incremental modifications. So this is by no means a comprehensive list, but this is kind of how I would think about doing quadcopter design. And specifically, ideally, we want a vehicle that can fly for a very long time, has reasonably high agility, and then also a very low cost. There's different ways of achieving these goals, but kind of at a high level, ideally what we want to do is minimize the mass of the vehicle without significantly reducing the maximum linear and angular acceleration the vehicle can produce. And then ideally not add any super complex mechanisms.
What about payload?
Yeah, so that I guess that would go into low mass. Like, of course, are you talking about like, yeah, I guess the usefulness of these vehicles is adding certain payloads. So the lower the mass of your vehicle, the more budget you have for adding a payload.
No, I guess what I meant is, if you might want to increase the mass so that you have enough, like, power to pick up a 5 kilogram package. I mean, lowering the mass by itself.
Oh, I guess I should specify here, I'm talking about like for a specific size of vehicle. So if you need to carry something very heavy, perhaps you move up in vehicle size, which of course would increase the mass, right?
Okay.
But if, given that you're like, okay, this is my, vehicle and I want to keep it this size, then and carry this payload, then like starting from that point, I guess, you don't want to be using like steel arms or something that are super heavy. Anyway, the point I want to get across here is kind of the central idea behind this talk. It revolves around this theorem. So the idea that there's no such thing as a free lunch. So in other words, for each quadcopter-like design that I'm going to show, the kind of main question you want to have in the back of your mind is, what exactly do I gain from making this design modification, and what does that come at the expense of? So that's kind of the big idea of or the main question you want to be asking here. So I'm going to start by talking about this first project. In this case, we're really interested in flying quadcopters in very extreme environments. So this started out by thinking about, how would we fly a quadcopter in, for example, a hailstorm, or maybe near a tornado where I have very large wind shear forces. And specifically, in this case, I'm only going to focus on environments with large torque disturbances. And the way that we're going to reject those torque disturbances is in part by using this angular momentum wheel. So here on the left, you can see this small wheel attached to the bottom of this vehicle. I'm also going to show a little bit of work on a much smaller vehicle, which has a little tiny cute momentum wheel on top, which the smaller vehicle is mostly just to show that this effect scales quite well with changing vehicle size. And the main reason that we're using angular momentum in this case to reject torque disturbances is that this effect scales with the speed of the wheel. So rather than needing to increase the mass of the wheel in order to reject larger torque disturbances, you can simply spin the wheel faster, which is quite a nice property. So I'll start by kind of showing what this looks like in practice, and then we'll go a bit into the math, or how it works rather. So here I'm going to first show a small ball bearing being dropped on the vehicle from above. So we've added these little paddles here. This basically simulates an impulse torque disturbance on the vehicle. And in this first case, the vehicle will be shown with the momentum wheel not spinning. So this is basically a conventional quadcopter. You can kind of see how that impulse torque disturbance affects the vehicle. And then in this case now, when we have the wheel spinning, you see that the vehicle produces this much more oscillatory motion. So again, on the left here, and I'll show this video twice. On the left is the vehicle without the wheel spinning. So that's a conventional quadcopter. On the right, you see the vehicle with the wheel spinning. And kind of the interesting thing that you see happen is by modifying the dynamics of the vehicle, we've coupled the roll and pitch states of the vehicle, which means that our thrust direction kind of oscillates around what it originally was after that impulse torque disturbance was applied. And so that allows the vehicle to keep its thrust direction closer to the vertical and reject these disturbances more easily.
Would you want that wheel to be spinning all the time, or would you want to sort of detect that a disturbance has taken place and then quickly start spinning that?
Right. So yeah, once the disturbances happen, then it's too late. But one nice property of this is you can turn the wheel off. So you can imagine a situation where if I want to be super agile and fly through a forest, I can turn my wheel off, and then essentially it's just extra mass that I've added. And then if I want to do some station keeping, then I can spin the wheel up and just hover in a desired position and be able to reject those disturbances.
Is it really too late once you detect a small change in? Is it too late to quickly start spinning that?
So yeah, I guess it kind of depends. It does. I mean, of course, it takes some time to spin the wheel up, and as you're spinning it up, that also applies a yaw torque. So then it's kind of like if you were to spin it up quickly, then you're applying this very large yaw torque that you'd also have to compensate for. So it's
How fast is that spinning?
For the large vehicle, we're spinning at 468 radians per second. For this small one that I'll show, it's 1,000 radians per second.
Wow. Okay.
And yeah, I'll talk a little bit later about how we chose those numbers. It's kind of interesting. So yeah, just to show what this looks like for the small vehicle, here I'm just dropping a very small 5-gram mass. This is without the wheel spinning. Here is with the wheel spinning, and we see, of course, kind of the same behavior as we would expect. So yeah, we did some small analysis that you can find in my dissertation of how this affects scales with vehicle size, but I'm not going to talk too much about that in this talk. So yeah, before I get into the details, I'm kind of going to skim a bit over the dynamics derivation because it's quite involved and tedious. But the main thing to note is that the momentum, the additional angular momentum, only directly affects the rotational dynamics of the vehicle. So, kind of the reason that's interesting is typically for quadcopters, we have this cascaded control structure here, where in the outer loop, we have a position controller. So that's taking in desired positions and desired velocities, and then running usually some PID control in order to output desired accelerations. And then from that desired acceleration from the position controller, we can compute a desired attitude. So that is basically the desired thrust direction of the vehicle, where our attitude controller is taking in the current attitude or the current thrust direction of the vehicle and basically trying to drive it to align with that desired acceleration direction given by the position controller, as well as achieving a desired yaw angle. So kind of the third block here is this thrust conversion block. So this basically takes the total desired acceleration, which is given by this desired thrust F sigma here, and our desired body torques. So these are the torques produced by the propeller written in the body fixed frame, and then converts those into individual thrust forces. So the reason I'm talking about all of this is basically to point out that because our angular momentum only really affects our rotational dynamics, in this case, we only actually have to modify this attitude controller for this vehicle. So we can actually use the same exact position controller as a conventional quadcopter uses, which is quite nice. So let's see kind of what that looks like. So here I'm showing the linearized rotational dynamics of the vehicle. So it turns out the rotational dynamics are actually very close to being linear. So there's a couple cross terms that I'm neglecting, but usually they're pretty negligible. And here I have phi and theta, which are the roll and pitch error between the current thrust direction of the vehicle and the desired acceleration direction that our position controller was giving us. And then phi dot and theta dot, which are our roll rate and our pitch rate, which ideally we would like to drive to 0. Here, tau x and tau y are the roll and pitch torques that'll be produced by the propellers, and j sigma sub xx and yy are the total moment of inertia of the vehicle about the roll and pitch axes respectively. And then this j sub w zz is the moment of inertia of the momentum wheel about its rotation axis. And this omega w is the angular velocity of the momentum wheel. So this term is basically the angular momentum of the momentum wheel divided by the total moment of inertia of the vehicle in either the roll or pitch axis. So this is assuming that we have a constant wheel speed. And what we kind of see is that as we increase the angular momentum of the vehicle, our roll and our pitch states become more coupled. And so that's what's introducing that oscillatory motion that we saw earlier when we applied the torque impulse disturbance. But once we have this model, it's very straightforward to synthesize an infinite horizon LQR controller, which is what we use for the vehicle. And more specifically, there's even kind of a nice feature of this structure in that we found we can compute the infinite horizon LQR feedback gain K as symbolically as a function of the wheel speed. So the idea is as I'm spinning my wheel up or spinning my wheel down, I modify my feedback gain matrix accordingly. And I do it in this way that doesn't require solving a Riccati equation online. So also quite nice. You can implement this on very, very cheap microcontrollers without any fancy computers. So yeah, I guess the follow-up question is then like, okay, this is great in experiment, but like theoretically, does this actually improve the torque disturbance rejection? And it turns out, yes, it does. And the way we show that is using an H2 norm analysis. If you're unfamiliar with the H2 norm, this is basically considered the cost to recover from an impulse torque disturbance. So if our cost is defined as so, where X is our roll rate, and pitch rate states, and this tau is the roll and pitch torques that we apply by the propellers. Basically, we see as we increase the angular momentum of the vehicle, so as we spin the wheel faster, the cost required to recover from that impulse, roll, or pitch torque monotonically decreases. So you might be thinking like, oh yeah, this is great. That means I'll just spin my wheel as fast as I possibly can and I'll get the lowest torque disturbance sensitivity. But of course, the problem then you run into is that you're storing a lot of energy in your momentum wheel. So as I mentioned earlier, I was going to talk a bit about how we chose those numbers for the wheel speed. In this case, we're only putting in as much kinetic energy into the momentum wheel as is, I think it's either equal or twice the maximum kinetic energy that can be stored in the propellers. So the idea is we want to keep this vehicle kind of in the same safety class as a conventional quadcopter. Yeah, so just kind of wrapping up, talking about the specific project, the big picture takeaway here is that the sensitivity to torque disturbances of a quadcopter will monotonically decrease with increasing angular momentum. But of course, by the no free lunch theorem that I mentioned earlier, the price we pay for this improved torque disturbance sensitivity is that we necessarily must slightly increase the mass of the vehicle. But the kind of benefit of this is because we're using angular momentum as our mechanism for doing torque disturbance rejection, that angular momentum scales with the wheel speed. So in principle, you could imagine a vehicle with a very lightweight wheel that spins very, very quickly. But of course, the lighter that we make the wheel, the more energy we have to store into it for the same amount of angular momentum. So there's some kind of trade-off to be decided there. I'm going to stop briefly. Are there any other questions about this project before I'm going to move on to talk about the morphing vehicle? Okay, great. So, all right, so now we're going to discuss the kind of second design tweak to the quadcopter. Here in this work, I'm going to describe a kind of novel design that uses unactuated hinges to enable flight in a few different new configurations that kind of enables the accomplishment of some of these tasks. I'll show videos of all of these tasks, so don't worry if these pictures are a bit confusing. This is largely going to be from our most recent journal paper, which we submitted to TRO. Although this vehicle is kind of a superset of our previous conference paper that we published. So yeah, basically the main idea behind this vehicle is that it differs from a conventional quadcopter in that each of the four arms are connected to the central body via an unactuated hinge. So we're not adding any special sensors that can measure the angle of the arms. We're not adding any other special components. This vehicle really is exactly the same as a conventional quadcopter, except for these hinges. That's really the only difference. And what we can do by adding these hinges is hover in a new configuration with two arms folded. So we achieve this by reversing the thrust direction of the propellers attached to the two folded arms. And now because the vehicle is designed such that those thrust axes are offset from one another, a yaw torque is produced that counteracts the yaw torque produced by the two unfolded arms. So previously we couldn't hover in this configuration, but now we can using this under actuation. So we can utilize this in a few different ways. Specifically here, we show the vehicle transitioning to the two arm folded configuration in order to traverse a narrow tunnel. So because the horizontal dimension of the vehicle is significantly reduced when flying in this two arms folded configuration, we can access areas that a conventional quadcopter would not be able to. So in this example, the vehicle can't traverse the tunnel in the unfolded configuration, and in your hover state, you basically have to fold your arms if you want to go through. Additionally, you can do other fun things such as traverse narrow vertical gaps by folding all four arms at once. So here, after a quick trajectory used to gain upward velocity, we reverse the thrust direction of all four propellers, which folds all four of the arms. And then while the arms are folded, we're controlling the attitude of the vehicle by varying those reverse thrusts. And then finally, we reverse the thrust direction of the propellers again, which allows the vehicle to return back to its kind of conventional quadcopter mode. There's two other tasks we can do, which maybe are less interesting, but also kind of nice because you get them for free. So here we show the vehicle perching on a hanging wire. This is nice because when we're in the folded configuration, the center mass of the vehicle moves below the central body. So basically we can perch on these wires without really modifying the vehicle or requiring any different complex mechanisms. And then another interesting thing that we can do is to perform some very limited grasping. So here I'm showing the vehicle moving a box from one location to another. So like after we land, basically the two folded arms can be used to firmly pinch the box and then move it to a different location. So I will note here that this is a very, very restricted task here. So this requires a very specially sized box. And of course, the mass of the box is also tightly constrained by the maximum vertical thrust that can be produced by those two unfolded arms when you're flying in the two arms folded configuration. But again, you kind of get this for free when you have a vehicle like this. So just kind of to reiterate, the main idea behind this design is that because it's almost identical to a conventional quadcopter, again, it only differs in the use of those hinges. We have basically the same power consumption of a conventional quadcopter when we're flying in the unfolded configuration. And I'll talk about this next point a little later, but basically the thing that you lose is your yaw agility when you add these hinges. Then again, I'll specify exactly why in a bit. So kind of the ideal use case for this vehicle that you could imagine if you're, say, doing a search and rescue operation where you need to fly a very long time in the unfolded configuration, but then say you reach a building with a doorway or a window or something that's too narrow to traverse, you can transition easily into this two arms folded configuration, pass through the doorway, window, whatever, and then return to your normal, very efficient operation in the unfolded configuration. So yeah, that's I guess the main idea of this project. So I'll very quickly discuss how this differs in terms of control of a conventional quadcopter. Specifically, here we have the exact same control structure that we had used for the momentum wheel vehicle. But in this case, we're going to modify this thrust conversion block as well as our attitude controller. And this basically comes from the fact that when we're flying in the two arms folded configuration, of course, our geometry is much different. So the mapping from individual thrust forces to the total thrust in the Z direction or about the yaw axis of the vehicle and the roll, pitch, and yaw torques will be very different. And correspondingly, we will need to modify our attitude controller to account for that as well. I will note very briefly, there are many other controllers. You could use some nonlinear control, some auto predictive control. This is just kind of like the simplest thing you can do. So yeah, there's different ways of doing this, but this is just kind of one way. So for the thrust conversion block, this really only depends on the geometry of the vehicle. So what we want to do is find a mapping, which turns out to be linear, from our total thrust F sigma and our roll, pitch, and yaw torques here to X, Y, and Z. And we want to find how those are related to our individual thrust forces. So this can be easily computed just from the geometry of the vehicle, plus some of the properties of the propellers that you're using. And it's computed as this matrix M. So this is a 4x4 matrix where the first row is denoted F or M sub F sigma. That's denotes how the four thrust forces relate to our total thrust in the Z direction of the vehicle. And then the bottom three rows are this M sub tau B, which relates the four thrust forces to your roll, pitch, and yaw torque. So as long as this mapping is invertible, then we can convert our total thrust and body torques into individual thrust forces. And as it turns out, as I mentioned earlier, how the two folded arms must have their thrust forces offset. Turns out this matrix is only invertible when you have that offset. So if you just have, you basically need your vehicle to look a little bit more like an H than as an X is a way to visualize that. So this will be different from each configuration. And then once you have that mapping, you can use it to very easily synthesize your attitude controller. In this case, again, we're using an infinite horizon LQR controller. Again, you can use other types of controller if you want. This is kind of the easiest thing that you can do that's easily implementable on microcontrollers. So here our cost for our LQR controller has our states X, which are roll, pitch, yaw, and roll rate, pitch rate, and yaw rate. In this case, Q is just a diagonal matrix where we rate have a lower cost for our roll and pitch states, as again, we want to align our current thrust direction with the desired acceleration direction that our position controller gives us. In terms of our input cost, this is the roll, pitch, and yaw torques times this cost matrix R sub tau B. So normally for a conventional quadcopter, this would just be diagonal perhaps adding an additional cost on the yaw torque, as the yaw control authority of typical quadcopters is usually small. But in this case, for the 2 arms folded or the 4 arms folded configuration, we don't want this to be a diagonal matrix. We want it to be weighted based on the geometry of the vehicle, which you can do very easily in this way. So here, this plus denotes the pseudo inverse of that m tau b. So those were the lower 3 rows of our mixer matrix, or thrust conversion matrix I showed on the previous slide. And then RU you can choose based on whether the propellers are spinning in the forward or reverse direction. The reason we do that is typically quadcopter propellers are only designed to spin efficiently in one direction. So for example, in our case, our propellers have a maximum thrust of about 7 to 8 newtons when spinning in the forward direction, but in the reverse that drops to about 3 to 4 newtons. So you'd want to have a higher cost for those propellers spinning in reverse. But basically, once you have this, then this becomes very easy to synthesize a controller based on the geometry of the vehicle plus those the costs for spinning your propellers in the forward or reverse direction. So one more slide about math, and then we'll go back to cool robot videos. So kind of the last piece of the puzzle then is, okay, if we design our attitude controller, assuming a specific geometry, how do we ensure that that geometry is actually valid? Because there's no actual constraints to prevent the arms from folding or unfolding, or there's no physical constraints. So we need to account for that using control theory. So as it turns out, if we look at the vehicle dynamics, which I will not here for brevity, but under some mild assumptions, we find that there exists a linear bound in terms of our total thrust and our roll, pitch, and yaw torque that, when satisfied, prevents the arms from either folding or unfolding, depending on which configuration you're in. So here, these constants, CF, CX, CY, and CZ, can just be computed using the geometry of the vehicle, as well as how the mass is distributed and the moment of inertia of the vehicle. But once we compute this bound, it gives us a way to ensure that, for example, if we're flying in the unfolded configuration, the arms will not suddenly start to fold. And so as long as this bound is satisfied, basically we can use any existing quadcopter trajectory planning, controllers, whatever you want. The only extra thing that we've really added is this bound on your control inputs. So what this translates to is basically a reduction of the maximum yaw torque of the vehicle. If you kind of look at the actual values of these constants, what you'll find is that when applying this bound compared to a conventional quadcopter at hover, your maximum yaw torque is reduced by about 36%. But your maximum roll and pitch torques are actually unaffected compared to if you just were to consider the bounds on the thrust forces themselves, and your minimum and maximum total thrust is also unaffected. So we're really not affecting the agility of the vehicle very much by adding these hinges. The only thing we're really doing is preventing the vehicle from turning around very quickly. So this kind of corresponds to, I think it's about a quarter second. It takes a quarter second longer to do a 180 if you're just hovering when you're using these hinges, if you want to avoid the arms folding. So kind of, a mild, I guess, reduction in agility here. So yeah, again, kind of the idea here is that by adding these additional degrees of under actuation, we can reduce the size of the vehicle when we're flying this 2 arms folded configuration or 4 arms folded configuration, and perform a few of these other tasks, and that the drawbacks really aren't too bad. So, you have this small reduction in yaw torque that you can produce, but in terms of the power consumption of the vehicle, it's almost identical to a conventional quadcopter when you're flying in the unfolded configuration. Although, of course, there is also this somewhat small increase in mechanical complexity by adding these 4 hinges. I'm going to pause here again. Does anyone have questions about this project? Otherwise, we'll move on to talking about some of the path planning projects.
Yeah, a quick question. Can you comment on what type of controller are you using in between the transitions?
Yeah, so the transitions happen fast enough that we don't actually, we aren't doing any control. That's also kind of complicated by the fact that we have no sensors to sense the angle of the arms. So it'd be very difficult to actually do control during the transition. But it happens fast enough that you can basically just switch controllers and then recover very, very quickly.
I see. So basically, you use the second controller to hopefully recover from the disturbance caused by the transition phase.
Right. Yeah, that's essentially kind of the idea. And in principle, I guess you could measure the angle of the arms if you wanted to, but here we're kind of looking at like what's the smallest change that we can make to enable these really useful behaviors. Well, any other questions? Otherwise, I'll keep going. All right. So now I'm going to move into the second half of the talk. Here we're primarily going to be looking at how we do very efficient continuous time collision checking between a given quadcopter trajectory and either convex obstacle, or later on I'll show for some previously unseen obstacles. So this first work is from this conference paper, and basically is the basis for the follow-on work that I'll show a little later. And to kind of give you an idea of when this type of planning is useful, I'm just going to show a quick video. So in this case here, we see a quadcopter that's encountering an unexpected obstacle that has to quickly bring itself to rest without colliding with it. So there's a lot of different ways that you can find collision-free trajectories, but kind of a common method is to generate a whole bunch of these candidate trajectories, which were shown as those cyan lines, eliminate the ones that collide with the obstacle, and then choose somehow the best collision-free trajectory to bring to avoid the obstacle. Actually, I'm going to skip this video for now. So the idea behind the planner that we're using in this case is the tried and true method, I guess, of doing sampling-based collision avoidance. So we're only going to be considering algorithms of this type, where we basically generate some candidate trajectory. In this case, we're generating these by randomly sampling positions in 3D space, and then finding trajectories that bring the vehicle from its current position to those positions, ending at rest, so ending with 0 velocity and 0 acceleration. Once we have generated some candidate trajectory, we can evaluate its cost. For this work, we're using average jerk, so that enforces kind of a sense of smoothness of the trajectories. And then after we check whether it's a lower cost than the previously found lowest cost collision-free trajectory, then we will check whether it collides with the obstacles. And this is really what we're focusing on in this work. So this is usually the most computationally expensive step. So if you're evaluating the cost, usually that's very trivial, especially if your cost is just evaluating the average jerk. But this is really where you run into the bottleneck in this type of sampling-based planning. And kind of the reason that we're doing the sampling-based planning, is that it's very easy to deal with non-convex spaces. So here we can go around either side of the obstacle. We don't have to like break our space into some convex polytopes or something. And then also we have some really nice probabilistic guarantees about optimality. So as we sample more trajectories with the probability approaching 1, we'll eventually find the optimal to rest trajectory. So yeah, before we talk about how we do the collision checking, first we need a model for our candidate trajectories. In this case, we're using a 5th order polynomial in time. So here x is the position of our quadcopter in 3 dimensions, and then c5 through c0 are some constants that are defined by the initial position, velocity, and acceleration of the vehicle, and as well as the position, velocity, and acceleration of the vehicle at the end of the trajectory. So again, here we're sampling, when we're generating these candidate trajectories, we're sampling different end positions with 0 velocity and 0 acceleration, and then different trajectory durations. That's what that capital T stands for. And then in the next slide, I'm going to show basically why we use that representation specifically. One other thing I should mention is because we're using 5th order polynomials, that corresponds to minimum average jerk, which is a kind of nice property. So, okay, a little bit of math, and then I'll show kind of a visual of how this collision checking method actually works. So the background here is that if we want to determine whether a trajectory crosses a given plane, we can do it in the following way, where we first compute our distance of our trajectory to the plane where here n is a unit normal of the plane and p is just a point along the plane. Of course, x here is our fifth order polynomial in position. Once we have this distance, we can compute the critical points of that distance as follows, where we set the time derivative of that distance equal to 0, find the zeros of this equation, and that gives us these two critical points here. And so what this is saying is basically between these critical points, we know that the distance of our trajectory to the plane is either monotonically increasing or monotonically decreasing. So if there's two critical points on the same side of the plane, we know that the trajectory does not cross the plane between those points. The reason this is nice is that because our position trajectory is the fifth order polynomial, when we take this dot product here, our distance is also a fifth order polynomial in time. And then when we take the dot product, it becomes a fourth order polynomial, which we can solve in closed form. So if you're unfamiliar, fourth order polynomials are the highest order polynomial that has an analytic solution, which means that we can find these critical points super fast. So we can find them in constant time because there's this closed form solution, which makes it very easy to find these points and determine which sections of this trajectory cross the plane. So the way we apply that, but before I go on, any questions about kind of the setup here, the background? All right, so the way we apply that, I'll show a quick animation. Here we have some convex obstacle, in this case, a circle, and our trajectory here. Note that we're planning a configuration space here. So typically model our quadcopter as a sphere with some radius, but in this case, we just inflate all of our obstacles by that radius and then plan as if we were a point mass. So the first thing we do is find a halfway point along our trajectory, and then we linearize our obstacle about that point. So when I say linearize, I mean we find a plane that is tangent to the obstacle and that has the this sample point in the obstacle-free side. So we've split our space into definitely obstacle-free space as well as maybe has an obstacle space, if that makes sense. From here, we can compute our critical points, which again can be done in constant time using that closed form solution of a fourth order polynomial. Once we have our critical points, then we can check which sections of this trajectory are definitely in the feasible space. So since both of these points lie on the same side of the plane, we can certify that section of the trajectory is collision-free, whereas this section lies on different sides of the plane, so we can't say one way or another whether it's collision-free, but we can apply this method recursively. So for this section, we can then find a halfway point, linearize the obstacle about that point, find our critical points, and then if all of these critical points lie on the obstacle-free side of the plane, then we can certify those as being collision-free. So kind of stepping back out to finish the algorithm, then we would check the other half of the trajectory. Here, this critical point lies on the other side of the plane. So again, we'd apply this algorithm recursively. And in this case, we'd find our trajectory is collision-free. So hopefully that wasn't too confusing. I hope the animation was at least somewhat helpful. So the question is, how fast, I guess, is this really a useful idea, I guess? So we did a small simulation here, just some Monte Carlo simulation where we basically placed a sphere randomly in the space and then planned trajectories that end in random positions and checked whether they collide with the sphere. So as you can see here, typically doing this collision check would take about half a microsecond. And kind of for comparison, it's a bit hard to compare this to other methods as there aren't that many collision checking methods that are specifically for fifth order polynomials that are continuous time, deal with convex obstacles. But I did find at least one other paper that was dealing with determining whether any order polynomial trajectory collides with convex obstacles, and for fifth order polynomials, their method would get about 50 microseconds. So in this case, we're 1 or 2 orders of magnitude faster than kind of the state of the art for other collision checking methods. So yeah, and again, the reason we want to be fast is the faster we are, the more candidate trajectories we can sample, so we can more densely sample our space and find more optimal trajectories for avoiding obstacles. So I skimmed over a lot of stuff in this work just to cut down on time. But kind of the key takeaway here is that we can do continuous time collision checking very fast. using this special property of fourth order polynomials and the sequential linearization of obstacles. And this also avoids a lot of the discrete time collision checking pitfalls. So normally, if you were going to do collision checking, you would discretize your path and then check each of those points for collisions with obstacles, which means you might avoid, you might not detect collisions with thin obstacles. Also makes checking with dynamic obstacles a bit difficult, but in this case, we can very easily deal with both of these problems. Stop one more time for questions here. Otherwise, I'll move on to our kind of extension of this work into the unseen obstacle domain. All right. Cool. So let me check how much time I have here. Oh, okay. I'll try to hurry up. So why is my picture not showing up here? Hold on. Let me reset this real quick. Okay, you should be able to see a picture of a quadcopter now. I don't know why it glitched out there.
Looks good now, yeah.
Cool, yeah, so in this section, we're gonna be talking about an extension of the work that I just discussed. Specifically, this algorithm that I developed called rectangular pyramid partitioning using integrated depth sensors, or rapids for short. And so the goal here is that if we have a vehicle that has a depth sensor on it, how can we plan collision-free trajectories very quickly given a single depth image from that depth camera in a way that can be run on very computationally constrained hardware. So we're really focusing on, rather than having a vehicle that requires a laptop level of a processor on board to fly autonomously, we want to be able to use very cheap, very low powered computers to still achieve very reactive autonomous flight. So kind of the system stack, if you will, for this vehicle looks as follows. So here we have a very fast low-level controller. So this would be something similar to what I showed in the momentum wheel and folding arms project, where we're just doing basically attitude control here and trajectory tracking. Above that, we would have a slightly slower but still quite fast layer that's tasked with doing collision avoidance. So here we have some sensor that's able to sense obstacles in the environment, turn them into some other low-level representation that then can be used for doing collision avoidance for the next, over the horizon of, say, the next few seconds. And of course, on top of that, typically you'd have some higher level planner. So for example, this high level planner could be a human giving waypoints to the vehicle, or maybe it's some exploration algorithm that's giving new exploration directions to the vehicle. But the assumption here is that this is very slow and does not deal with obstacle avoidance. So in this work, we're specifically looking at this middle layer where we're getting depth images from a depth camera and then finding collision-free trajectories that ideally are chosen such that they achieve some goal given by the high-level planner. So let me get my laser pointer back. Yeah. Okay, so I'll go another quick kind of visual description of this algorithm. So what I'm showing here is a side view of a depth image. So you can imagine a depth camera being here looking to the right, where each of these little vertical lines is a pixel in our depth image, which denotes the obstacle space, and the distance from the camera to those pixels is our free space. Here again, we're modeling our quadcopter as a sphere with some radius, and we additionally include some field of view constraints. So we assume that there's some obstacle just outside the field of view that we don't want to collide with. Similar to our previous work, we were using a sampling-based planner again. So here, the assumption is our sampling-based planner gives us a candidate trajectory. Again, these are two rest trajectories that bring the vehicle to a stop at the endpoint. And then once we want to evaluate this candidate trajectory for collisions, what we do is split the space into a series of rectangular pyramids. So this kind of green triangle here, in 3D would be a rectangular pyramid, in 2D it's just a triangle, is generated by just doing this kind of spiral search in the depth image. There's more details in the paper on how we actually generate these pyramids, but once we've generated this pyramid, we ensure that it contains the endpoint of our candidate trajectory. So the idea here is if I were to sweep my sphere along this candidate trajectory while it's inside the pyramid, I should not collide with obstacles or the unknown space, if that makes sense. So the trick here is once we've got this pyramid that describes the free space, it's basically trivial to detect where our trajectory collides with the lateral face. Reason for this is that we're using fifth order polynomials to describe our trajectory. And we already know where one of the roots is. So at time t equals 0, we know that one of the zeros of that, the equation for the distance of the trajectory to the lateral face of our pyramid is at time t equals 0. Sorry, that was a bit of a mouthful. And so then finding where the trajectory collides with the lateral face of the pyramid amounts to solving a fourth order polynomial, which again, we can do in closed form in constant time. So once we find where this trajectory collides with the sidewall, we can basically apply this algorithm recursively. So now we can generate a new pyramid at a slightly shallower depth. And then if this pyramid contains the rest of our candidate trajectory, then we can declare that section of our candidate trajectory to be collision free. Basically, if we cannot generate a pyramid, then we would declare this section to be in collision with the environment. So just kind of a reminder of the setup of what we're doing here. Basically, we get a depth image, we generate candidate trajectories, and then as we're checking them for collision, we generate these pyramids, which can be reused within the same depth image. But after we've chosen the best collision-free trajectory, we'll apply the first section of the best candidate trajectory in a receding horizon fashion, and then a new depth image will arrive and we'll start this process all over from scratch. So this is a totally memoryless planner.
Nathan, just a quick time check. Let's make sure we have a moment for questions as well.
Oh, okay. I might skim over a few things. I'm going to skim over some of the pyramid benefits, I guess. This is really nice because, you can reuse the pyramids. So like the idea here is instead of having a very high dimensional description of my obstacles, i.e. an entire depth image, I can have this very low dimensional representation, say 2 or 3 pyramids, which allows me to do extremely efficient collision checking. So I can generate many candidate trajectories without expending a lot of computational budget. How fast is this? Well, we compared this to a couple other sampling-based methods. So these are the best reported results from a couple other methods that use a different way of checking for collisions between these polynomial trajectories and a depth image. And as you can see, in this situation, by doing this decomposition of the space into rectangular pyramids, basically we get an order of magnitude speed up, even on very constrained hardware. So here in Odroid, if you're not familiar, is basically like a Raspberry Pi, very, very cheap. It's about a $60 embedded computer or something. So I'm going to show some experiments, and then that'll be pretty much the end of the talk. The setup here is we're using a depth camera on board a quadcopter. We're using this Odroid computer, again, very cheap computer. That's kind of the whole idea, is because this is computationally efficient, we can use this very cheap low power computer. And then we're getting position and attitude estimates from this tracking camera. Excuse me. So yeah, in these videos that I'm showing, the vehicle is totally autonomous. Here we're capturing depth images at 30 Hertz, and then we're running our planner for 30 milliseconds after each depth image arrives. In this case, the cost function we're using is basically we want to move as fast as possible down the hallway until we can't find any collision-free trajectories, at which point we turn 90 degrees and continue. And so here the hallways are about 20 meters long, about 2.5 meters in width and height. And the idea is here this low-level rapids planner is giving us a collision avoidance guarantee, and someone else can design some high-level planner where they don't have to worry about doing collision avoidance. So very quickly, I'll show what this kind of looks like from on board the vehicle. On the left here, this is just the color video image feed of the vehicle flying down the hallway. On the right, this is the depth images that we're feeding into the planner, and then this is just a visualization of what the planner is actually doing. It's a little bit hard to see, but these kind of blue pyramids are the pyramids that we're generating, and the cyan line is the trajectory the vehicle is currently tracking. In this case, for each depth image where we were able to find a collision-free trajectory, we evaluated about 2,000 candidate trajectories, and on average generated about 3 pyramids. So that really tells you kind of like it's pretty easy to describe this complex space using a low number of pyramids, and that allows you to check basically thousands of trajectories for collisions. So yeah, and some other statistics, we're traveling about 40 meters in 43 seconds with maximum velocity of about 2.6 meters per second. So not incredibly fast, but still quite quick. Yeah, so I'm gonna, I guess, do some quick closing thoughts about kind of the entire dissertation, and then open up the floor for any additional questions. Again, the main idea here is that it's possible to improve the utility of quadcopters using a different combination of different design control techniques. So first I talked about this angular momentum vehicle that reduces your torque disturbance sensitivity, and then this passively morphing vehicle that allows us to fit through narrow gaps and do perching tasks and some limited grasping. And then finally, I discussed this collision checking method, which reduces the computational hardware requirements of the vehicle. So we're able to do autonomous flight with much cheaper, much lower power computers. Of course, then bring it back to this no free lunch theorem that I brought up. Of course, there are some trade-offs here, but these trade-offs are usually somewhat minor. So for the angular momentum vehicle, we found that that effect scales with the wheel speed, meaning that we only need a very modest increase in the mass of the vehicle. And for the morphing vehicle, we saw that the bounds we had to enforce to prevent the arms from folding when in the unfolded configuration only really reduce the maximum yaw torque of the vehicle. And that's typically a modest amount, in our case, 36%. Finally, for the collision checking method, I mostly talked about using sampling-based planners. So these, of course, aren't ideal for all situations. For example, if you want to do some time optimal trajectories, say for drone racing, you might want to use some different optimization techniques. But for just general autonomy, this works quite well. With that, I'd like to conclude my talk. I have an acknowledgement slide, but I figure I'll do it at the end after taking some questions. So does anyone have any questions about any of the stuff I covered?
So Tomlin's group does a lot of, safe sets and, computation of safe sets. Is it that, in her case, she's looking at a dynamical system that's a little complicated, and in your case, you have, the dynamics of the quadcopter are very simple. You're just going in a straight line, or, going, is there some relationship between all this work on safe set computation and what you're doing?
Yeah, so I guess the viewpoint that we've kind of taken here is a bit more deterministic. So, or I guess I'd argue maybe a bit more of an engineering approach. So when you in these pyramids, when you say detect that it's not going to work because the trajectory conflicts with the pyramid, and you find that point and you back off. How much do you back off by to calculate you from P2 to from P1 to P2, the pyramids you drew? How do you so what do you mean by back off here?
Go back there. You have P1. You see, the P1 doesn't work because of the collision with the boundary of the pyramid there that you calculate very quickly.
Right.
And how do you decide on P2?
So you do it exactly the same way. So basically, once we find this point where we collide with the sidewall of P1, we apply the same pyramid generating step for this. So we basically, instead of treating our trajectory as this entire thing, we're just treating it as this single segment. So yeah, you can basically we're basically just doing a recursive kind of thing. But yeah, I guess the difference here is like, I think the stuff Tomlin's group does is looking more about like, doing some reachability analysis. We're not really doing that here. We're just assuming that we can track this position trajectory with some accuracy bound.
Very good.
Hey, Nathan, can you hear me?
Yep.
Yeah, so I was wondering for the first project you had, the momentum wheel, why didn't you do that with like a propeller, and then you'd have extra thrust, and then you might be able to
Yeah, I think that's an interesting idea. There was someone else had done sort of a similar work. I believe that So I don't know if they made much progress on it. One of the problems with using a propeller is that you'd then be generating very large yaw torque. So there's some air drag on that propeller, and then basically the yaw torque of the vehicle wouldn't be balanced anymore. There's ways around this, maybe instead of using, so currently for quadcopters, you have 2 propellers that spin clockwise and 2 that spin counterclockwise. That way the yaw torque is balanced for the propellers. So you can imagine a vehicle where if I have one big propeller that's like my momentum wheel and 4 smaller ones, maybe I spin the big one clockwise and I spin all the smaller ones counterclockwise. But kind of in the current form that you wouldn't want to be like constantly having to counteract the yaw torque produced by the momentum wheel.
I see.
Any other questions? Okay, should I quickly do some acknowledgements, and then we'll wrap this up.
I'd like to ask, maybe before you do the acknowledgements or afterwards, we should have everyone turn their cameras on so we can take a photograph.
Yeah, here, I'll do the acknowledgements and then we can do that maybe, because I can't see Zoom right now, so because I'm in presenter view. Yeah, so I'll try to keep this real short, but no PhD seminar would be complete without acknowledging all of the help that I've gotten over the years. Mark, you've been such a fantastic mentor. I'm really grateful for the time you spent helping me improve both my technical abilities, but also just all the fantastic advice regarding my PhD and just general career. So yeah, I think like you mentioned earlier, I was extremely excited to join your lab. And I gotta say the excitement never really went away. So, thanks for making my time here really memorable. I also want to thank my lab mates, of course. I've had a blast working in the lab. Everyone's been super supportive and willing to help me solve even the smallest of problems. So I really enjoyed befriending you all, and I hope we stay in touch for many years to come. So yeah, with that, I'd like to conclude my talk. Then thank you everyone in the audience. A lot of my friends showed up. You've really made time at Berkeley quite special. So I'll stick around for a bit longer for questions, but that should conclude the talk.
Well, congratulations, Nathan. I'd like to ask everyone to quickly turn on their videos if you don't mind. Let's just take a photograph.
Are you going to count us down for when to smile?
Well, just, give us your best smile all the time, I guess. No, I'll count you down. Okay, 1, 2, 3. Let's go take another one. Okay, hang on. Let's do another one. Hang on. 1, 2, 3, go.
Well, congratulations, Nathan.
Thank you. It's been a good time.
And I hope to see many of you guys this evening at the ME party. I think, Nathan, you will be there, so it'll be a nice celebration.
Okay.
Thank you.
There you go.
Great work, Nathan. That was really nice.
Yeah, thanks.